Good morning. Today we will study about reaction intermediates. Reaction intermediates are important to interpret the major products formed in a particular reactions, or I can even use them to predict all possible products formed in a reaction. As per the requirement of a question, we'll use them. But to interpret the reaction mechanism and how it will proceed, what will be its kinetics, we need to know about the reaction intermediates, how they behave, what are their types. So let's start. Reaction intermediates. Reaction intermediates, what are reaction intermediates? So reaction intermediates are the species which are formed during the reaction and are consumed there itself. They are never the product. They are formed during the reaction from reactants and are consumed there itself in the formation of product. Such species are called reaction intermediates. Okay, from the starting reactant, there would be some steps involved in which intermediate is formed, and then in some other step, it is consumed to form the product. Now, this is my simplest possible representation related to reaction intermediate. Otherwise, it is not that only one intermediate or always an intermediate will be formed in the reaction. Okay, it is not compulsory that it is always going to be a reactant intermediate involved, reactive intermediate involved in a reaction. Okay, but yes, if it is involved, then it is formed from reactant and then is converted to product. In a multi-step reaction, there is always a possibility that starting with reactant, first there could be intermediate 1, it may convert to intermediate 2, and so on, and it depends, and finally we get a product. Okay, now what is so important about reaction intermediates? Basically, I said reaction intermediates control the total formation of products. Now, if they control the total formation of products, how they control the total formation of products? I hope you all are aware of a little kinetics requirement in understanding this reaction mechanism. Okay, in understanding of this reaction mechanism, if we would know small amount of kinetics, it would be good. Assuming a reaction is a first step reaction, this first example that only one reaction intermediate is formed. Okay, assuming that reaction to be endothermic, I'm uh, I'm drawing a general energy scale. This is my intermediate 1, and then it is converted to product. This is a possibility. Here is the energy coordinate. Here is the progress of reaction. Same way, here is the energy, and here is the progress of reaction. Usually this energy is the free energy delta G. Okay, so it is an endogonic reaction. So there are two possibilities that this. Now you can see in this the second peak is higher, in this the first peak is higher. Okay, so both the steps are absorbing the energy from the surrounding. Overall reactions are endo. Now see, here this reaction, that is the second step, will behave as RDS, whose energy barrier is higher. Okay, and here first step will behave as RDS. This is our intermediate. Okay, so if first step is RDS, what I will study for the growth of the reaction is how can I stabilize the intermediate. If intermediate is formed at faster rate, RDS will start happening at a faster rate, and overall progress of reaction or rate of the reaction will increase. Whereas if the reaction graph is of this type, that second step in this particular two-step reaction is RDS, then my sequence of thought will be how unstable this intermediate would be so that it will react faster. Okay, it will react faster towards the second reaction, and thereby my second step is becoming faster and faster. So overall, I have to deal with the intermediate this way or that way. Okay, so how do we come to know which intermediate is involved? Well, which intermediate is involved depends on very indirect methods. We study the product forms, we study factors affecting reaction, factors affecting reaction rate, we study factors affecting reaction yield. For example, temperature, if I increase or decrease the temperature, what happens? Product reactant variations, if I change the reactant, is there any impact on pressure, solvent, medium, etc. So we study the effect of these variable factors on the rate of the reaction. Based on several observations, we conclude what is the possible, what is the probable intermediate involved in this reaction. Similarly, we study the effect of all these on yield of the reaction. Okay. Then we also study about the stereochemistry of the reaction. That also give a very important insight towards the fact that whether the intermediate is involved is a planar, non-planar, whether the reaction proceeded through the known carbocation, carbonine, etc. intermediate, or it did not involve one. So after studying all these indirect methods, we have concluded that there are certain specific intermediates involved which cover almost 98% of the reactions. Okay, we call them as a major reaction intermediates. I'm not saying these are the only intermediates involved, but major reaction intermediates involved in the organic reactions usually are carbocation, carbanion, carbon free radicals. I'm not writing free radicals. Okay, I'm writing carbon free radicals, carbene, nitrene, and benzene. And out of these six, if I would conclude, they cover almost, I can say 90% of our reactions required. These total will go for, say, 10%. And I may be still very humble in presenting this representation. 90 is to 10. It could even be more than 90 for carbocation, carbanion, and free radical reactions involved. Out of this, benzene mechanism is clearly mentioned in our JE syllabus, that it is excluded from JE syllabus. Okay, so we may not know much about its reaction mechanisms, but we should be aware of its bonding and basic formation of benzenes. Okay, so let's start with our reaction intermediates. The first one is first one is carbocation, but before proceeding to that, I would like to give you a general idea of what type of bond fissions are involved in a particular type of reaction intermediate formation or overall in any reaction. First is a homolytic bond fission. Assuming there is a covalent bond A and B, both had this type of shared electron pair. So if out of these, the breakage is like this, that A takes its electron, B takes its own electron, okay, then this is called homolytic. Homolytic can be achieved by either help of photons, then it is called photolytic, can be achieved by heat, then it is called thermolytic, or it can be achieved by some redox. So we have different methods to have this. But as a result of a homolytic fission gives us free radicals. As a result, free radicals are formed because there is no charge on the intermediate form. These free radicals are charge-wise neutral. Okay, and so these type of homolytic fissions are usually preferable in either non-polar solvent conditions or gaseous state. Either in non-polar solvent conditions or in gaseous state, they are preferred. They are easy, their bond energy is lesser. Heterolytic bond fission. If I have similarly A to B, I assume A is more electronegative than B. अगर मैं assumption लूँ, if I take this assumption, then as a result of heterolytic fission, I will form A minus and B plus. I'm writing two electrons but putting one minus only because one electron was originally from A only. So no further charge will accompany along with that. Okay. Is it clear that I'm writing two electrons but charge is only one? Only one electron came outside of A. It was originally from B. So charge imbalance of -1 is created on atom A. So A minus and B plus. In a heterolytic fission, products are ions. Ions are produced. Ions are produced, so it will be favored in polar solvent. In polar solvent, it will be favored. Okay, non-polar solvent, it will be avoided. In solvent, it will be favored. Let us move to carbocations. Now, what are carbocations? Well, carbocations are positively charged carbon. Okay, carbocations are positively charged carbon having 6 electrons surrounding it. Having 6 electrons surrounding it and one empty p orbital. This 6 electron surrounding, I would like to add it 6 bonding electrons surrounding it. 6 bonding electrons surrounding it and one empty p orbital. General representation we have already drawn. Okay, let us go to other possible shape and hybridization factor. Shape and hybridization of carbocation. First, if it is having 3 sigma and 1 MTP, then it is going to be sp2 hybridized. And when it is sp2, it is going to be trigonal planar. Okay, there are so many example of this series, CH3 plus, R3C plus, etc. If I have a condition where it has 2 sigma 1 pi, 2 sigma 1 pi and 1 empty p orbital. Okay, 2 sigma 1 pi and 1 empty p orbital, then it is sp hybridized. It is going to be linear. Okay, 2 sigma 1 pi sp hybridized linear. Example is vinyl carbocation. Vinyl carbocation is CH2 double bond CH positive. See this carbon. 2 sigma 1 pi and 1 empty p orbital. ठीक है, 1 empty p orbital. Is it clear? So there are different possible shapes and hybridizations of carbocations. Okay. Now, after this shape and hybridization, let us go to how a carbocation could be generated in a reaction. How it is generated in a reaction, generation of carbocation. Well, it entirely depends, but all I can say is there is going to be a heterolytic bond fission. It is a very gradual process. Never ever you come across that a bond fission takes within a seconds and all those things. It is just a one-step direct process. No. Let me exemplify. If I have, say, this is the leaving group, you can imagine in place of L, Cl, chlorine. L is what I'm taking is a leaving group. This is going to leave my carbocation. This is what my target reaction is. Okay, this is what should happen. But to take this step, there is a very important role how and why this sigma bond will break. Okay, how and why? So let me tell you that if I have something like this, there must be already a type of polarity within a molecule. Let me take example of water as a solvent. Water, solvent. Now when water approaches, then L will be surrounded by its positive poles facing L, like this. H, O, H, H, O, H, H, O, H, and so on. Okay, and its negative poles will be surrounding the plus end of the molecule. So basically, whatever polarity was there in the structure will be further enhanced. This bond will become longer, and this will become more del plus, this will become more del minus. This will be enhanced. Maintaining the solvent as I shown you in the first diagram, they are like this surrounding all over. Okay, as and as the steps will proceed, as and as the things will proceed, this bond will become longer and weaker due to presence of this solvent. Okay, this bond will become gradually longer and weaker. L further del minus del plus, and gradually same solvent remains like this. Solvent is there to surround our del charges. Then a stage comes when this is much positive, this is much negative, bond has become very poor, and a solvent has begun sweeping in between the two atoms. This is a solvent separated ion pair. What is this? Here we have got a solvent separated ion pair. Once this stage has reached, now it becomes relatively even more easier for the molecule to break down these two into complete carbocation. Of course, their original bonds, which so were there L minus, complete carbocation and anion. Solvent will be surrounding here like this. This L minus will be even more surrounded like this. Okay, so there is a very important role of solvent. If solvent was not there, this starting point, that is the polarization of a already polar bond, would not have taken place. Okay, it would not have taken place. It took place only because of help of solvent. This solvent supported this whole process. So that is why for a formation of carbocation, we need polar conditions. We need polar conditions, and I can say more polar the solvent conditions are. More polar the solvent conditions are, more polar the solvent, easier. What is the term easier implies? Easier means it is less activation barrier, easier to form carbocation. Okay, more polar the solvent, easier will be it to form the carbocation. That is how solvents should be in a role if they are they are there in helping the carbocation. So we need a heterolytic bond fission, and for that we need polar solvent which will support this heterolytic bond fissions. Okay, once they are formed, the other factor I would like to say that okay, we have taken a proper solvent, but as and as this carbocation stability increases, as this carbocation stability increases, this type of polarization and bond fission further becomes easier and easier. So, how the stability of a carbocation increases? What are the factors affecting the stability of carbocation? Well, there are several factors. Just some important ones are certainly first, I would like aromaticity. If there is any plus charge coming in a particular carbocation, it will definitely be very stable. Say this one. These are aromatic carbocations. Certainly, they are very stable. Okay. Second, I would say ki if there is resonance, yes, resonance supports the stability of carbocation. Example for resonance will be PHCH2 plus, CH2 double bond, CH single bond, CH2 plus, R CHOCH3 plus. Here this oxygen lone pair will give a bond to carbon and complete the octet. So these are all resonating. Third, there will be hyperconjugation. More the hyperconjugation effect my molecule, my carbocation will get, more stable it will become. Example is CH3, C positive, CH3, CH3. Fourth is inductive effect. Inductive effect. As our carbocation is electron deficient system, so plus I effect is good for stability of carbocation. If there is a plus I effect, it is good for the stability of carbocation. If there is a minus I, the reverse effect will take place. It is bad for the stability of carbocation. Okay. Besides this, certainly there is a hybridization factor. Hybridization factor. What does that mean? That when I have Me3C plus, this is sp2. But when I have phenyl P plus, or I have vinyl P plus, then these are sp. If they are sp carbocation, more the percentage S, more will be the electronegativity of the hybrid orbitals bearing these carbocations having this particular species. So overall, here the plus is present on more electronegative atom. That increases the electronegativity of that atom also. Here it is less electronegative. So plus on less electronegative is more stable than plus on more electronegative. Okay, so sp2 carbocation more stable than sp carbocations. Okay, sp2 are more stable than sp carbocations. Then there is one factor, there is a one particular factor, sixth point we should write, is something called dancing resonance. This fifth factor is a very specific phenomena. Okay, it is not a general phenomena, it is very specific and is almost limited to the molecule I am taking. It is in cyclopropyl methyl carbocation. Okay, it is present particularly in cyclopropyl methyl carbocation. So now what is there in cyclopropyl methyl carbocation? In case of cyclopropyl methyl carbocation, if I could write CH2 plus here, okay, these bonds, let me say C1, C2, C3, C1, C2, C3, C4 are bent bonds. C1, C2, C2, C3, C3, C4 are bent bonds. They are intermediate between sigma and pi. They are not on the internuclear axis of the two atoms. Roughly, they are bent by approximately 21 degrees from this internuclear axis. Okay, so those bonds are found to be parallel to the MTP of this CH2 plus. As a result, they show overlap of bent bond with our MTP orbital. This type of ring opening contributing structures will be observed. Okay, so this particular phenomena is called dancing resonance. It is not observed in all. Okay, it is not observed in all. This is not like in any cyclic system we will observe this. It is a specific phenomena for cyclopropyl methyl carbocation. The moment you move to cyclobutyl methyl carbocation or pentyl methyl carbocation, they are back to normal. No such phenomena will be observed. Okay, so dancing resonance brings unexpected stability. After considering all these, the overall stability, which is based on the different bond energies data which have been taken, is see 3 cyclopropyl attached, maximum dancing resonance, 2 cyclopropyl attached, less than 1. But as you can see, the overall, the most stable factor is dancing resonance. Okay, then comes the normal resonance. PH3C plus, why I have highlighted it, I'll tell you later. Okay, 3, then 2. Now here is an important junction. Please mark this. Important junction in case of carbocation stability. See, 3-degree carbocation is more stable than benzyl and allyl. Okay, 3-degree carbocation is more stable than benzyl and allyl. But yes, 3-degree, if it is 3-degree allyl carbocation, then it is more stable than normal 3-degree. Otherwise, due to 9 alpha H and Me3C plus, It is more stable than benzyl and normal allyls. Okay. Then comes the 2 degree. Then comes the 1 degree. And lastly, the methyl carbocation. Okay. So this is the overall stability order of the carbocations. Another very important structural feature that increases the carbocation stability. Always remember this one. Whenever there is a plus which is adjacent to second period atom, okay, second period atom, which is certainly now called heteroatom, bearing an unshared pair, see oxygen lone pair. Okay, if there is something that is present there, unshared lone pair के साथ C plus, then due to this type of resonance, okay, then due to this type of resonance, such carbocations are very stable. Okay, this results in a complete octet carbocations, which brings them a lot of stability. Point number 2 to be noted very carefully is bridgeheads cannot acquire sp2 hybridization. As a result, it is very difficult for bridgeheads to form a carbocation. Okay, as a result, it is very difficult for bridgehead to form a carbocation. Now, what does it say? Now, now in case of bridgehead carbocations, what happens is, see, there is a rule called Brett's rule. Brett's rule, which says that a bridgehead of a bicyclo compounds cannot become planar. Yes, the relative ease of that planarity increases with increase in size of bridges. So first, let me tell you what is this bridge head word meaning. See, this junction, which is common to both the rings, is known as bridgeheads. Okay, bridgehead could be like this. These are the bridgeheads. These are the bridgeheads. Okay, if I place plus here, it will be unstable. If I place plus here, it will be unstable due to strain. If I give plus to a bridgehead position, it will become very unstable. Yes, as compared to this, I can say that if I increase the size of the bridge, what is bridge? Bridge is the number of carbons connecting the two bridgeheads. Okay, here it was 2, 2, 1, here it is 2, 2, 2. So if I have a relatively longer bridge, comparative ease is more, but I still cannot say that they are very stable. No. Just a relative comment I can say that yes, as compared to smaller ones, it is easier for them to form a carbocation at this bridgehead. But always remember that molecules in general would like to avoid plus charges. Okay, we'll always like to avoid plus charges at these junctions because it creates a very high strain in molecule overall. If we keep such positive charges at these bridgeheads, then certainly the molecules are destabilized due to very high strain at these junction points. So, in general, molecule avoids having plus at these bridgehead centers. Okay, so that makes them, despite being 3 degree, it will be unstable. They cannot be handled by normal 1 degree, 2 degree, 3 degree factors. Okay. The note number 3, these are the important notes I will write, that what sequence we are, important notes to be kept in mind. First, a plus present at heteroatom having a lone pair is stable. Point number 2, bridgehead cannot form a carbocation easily. I would rather add the word easily. The problem with the bridgehead, yes, I cannot say that it will never form, but the ease will definitely be less. Okay. And the point number 3, if you remember here, I marked pH3C plus. I said I'll tell you later. So what is this pH3C plus is so important? Actually, what we would expect this structure to be is a planar structure. Okay. Our expectation for this structure is it is planar, and all 3 rings are resonating simultaneously, are resonating with C plus with equal ease simultaneously. But that certainly is not the fact. Why? See, if I make a C plus and these 3 rings like this, then their hydrogens which will head like this. As a result of this, there will be high repulsions. Now, these rings cannot be in the same plane of each other. Okay, so as a result, they becomes non-planar. As a result, they becomes non-planar, and they are basically what should I say, propeller shaped. Okay, these structures are propeller shaped. Propeller shaped. Yes, it is very stable. Okay, they are overall very stable, but not as it could have been. Okay, due to steric hindrance. If they could have been planar, definitely there would have been a further increase in the resonance energy and the stability of triphenyl methyl carbocation. But in nature, they are not found to be so. Same will be the case when we'll go to carbanion, okay, and free radicals. So if I say how they will be all inclined, I want all of you to imagine these planes, okay, slightly tilted. These planes as slightly tilted. Now, how can I exemplify the word propeller? You all might have seen this type of fan, propeller fan structure in big ships, or in aeroplanes, or a slight less propeller in fresh air fans that we use in kitchens and bathroom. They are all examples of propeller shapes. So these are not all planar. But at any point of time, this C plus can be in the plane with the rest of with one ring. C plus with this ring. C plus can be in a plane with a ring. But all 3 rings are not in a plane with each other. Okay, so just remember this, very important. A question may directly come, which of the following structure is a planar structure? Cyclopropyl methyl is relatively more planar, okay, but not overall planar, but relatively more planar than this one. So that brings us to the closure of general carbocation chemistry. There is a very important thing about carbocations that we'll study later in reaction mechanisms is rearrangement of carbocations. Carbocation always rearrange themselves from 1 degree to 2 degree if possible, 2 degree to 3 degree if possible, and further, provided at each and every possible step the new carbocation is more stable than the previous. How it takes place, we'll study later in reactions. Moving to carbanions. Now, the carbanions are C minus. Okay, C minus. They are also formed by heterolytic bond fissions. They are very important. What should I say? They are very important in study of organometallic compounds Example, Grignard reagent. Though I cannot say the formation of Grignard involves formation and as well as reaction, always involves only carbon ion. There are definitely involvement of radicals also. There is certainly involvement of radicals also, but yes, the structure finally said is usually referred as um, an ion. Okay, so coming to carbon ions, they are again formed by heterolytic fissions. They are studied in organometallics like RMGX. Okay, let us come directly to the major and most important part is structure and stability. Okay, as far as its structure is concerned, structure is first, I would say it have sp3 but pyramidal geometry. sp3 and pyramidal is like ch3 minus r2ch minus r3c minus, etc. It can have sp2 and trigonal planar geometry. Okay, sp2 and trigonal planar geometry is in such structures. Okay, it can have sp2 and bent shape geometry, sp2 but bent shape. Then I would say rch double bond ch like this, or phenyl. Then it has sp2 and bent. Point number 4, it can have sp. Habitually I'm writing this capital, it is not capital beta. Whenever we write hybridization, these should be always small. Orbitals are always represented by small letters. So sp, then it is linear, rc triple bond c minus. Okay, so for you, the major difference to be noticed is sp2 with planar and sp2 with a bent geometry. Okay, coming to factors affecting its stability. Factors affecting stability of carbon ion. Similarly, if there is aromaticity, it could be very stable. Okay. Let me give you example of aromatic carbon ion is cyclopentadienyl anion, cyclobutadienyl anion, etc. Number 2 is resonance like allyl, PHCH2 minus. These are all stable. There is no hyperconjugation, but yes, if there would have been reverse hyperconjugation, then it could have been of some importance, like CCl3CH2 minus. Here it is reverse hyperconjugation. Number 4 is inductive effect. For stability, I can say directly depends on minus I groups. More the number of minus I groups, more will be the stability of carbon ion. Okay. Number 5 is hybridization. as it is an electron dense species, right? Carbanion. So, more the percentage is in the hybrid orbital, more will be the stability of carbanion. Okay. Sixth is presence of atom with empty with empty d orbital at adjacent to C minus. Okay, adjacent to C minus. So let us take example. CCl3 minus will be more stable than CF3 minus due to this d orbital presence. Okay, considering all these factors, the overall stability of carbanions is found to be C-terminal alkynes are acidic. That fact is used here. Triple bond minus, phenyl minus. Okay, these are stable. Then comes the phenyl. Okay, then comes cyclopropyl. These are all very stable carbanions. Okay, these are all very stable carbanions. And then here you could have had a resonance one, that is PHCH2 minus, then CH2 double bond, CH single bond, CH2 minus. Then comes all these, one methyl, then ethyl, isopropyl, and tert butyl. Okay. Presence of these groups decreasing order stabilizes the carbanion. What do I mean? That if I have CH2 minus adjacent to nitro will be more stable than CH2 minus adjacent to R, and so on. Okay, this is what I meant by giving you this order, that the presence of these group adjacent to C minus in general stabilizes anions in this decreasing order. See, these R and H, they will not give any resonance or any minus I till halides. This is halide. This is halide. Till halide, I'll have either the empty t orbital resonance or I'll have a minus I. But in H, no minus I, no plus I, no minus R, no plus R. R, that is alkyls, there is no resonance. But yes, there will be more destabilizing phenomena called plus I. So all these are destabilizing in the last two. So they are last in the series of stability of carbanions. And in case of carbanions, there is no problem with its ease of formation at bridgehead. Carbanions at bridgehead can be formed. Carbanions at bridgehead can be formed. Okay, because it is sp3 carbanion. These three will be directed up, this will be directed down. It can be formed. Yes, there is plus I and all those factors, that is true. But it can be formed. Okay, so this was our carbanion discussion. Now let us move to next point, that is free radicals. Okay, let us move to free radicals. If I say the word free radicals in general, it is too vast. So I will limit myself to carbon free radicals. Okay, because free radicals could be anything. Free radicals could be anything. It could be F dot, fluorine dot, Cl dot, Br dot, I dot. It could be phenoxy dot, PHO dot, hydroxy dot, alkoxy dot. So many possible different types of free radical could be found in nature. Okay, but we are talking only and only about what? We are talking only about carbon free radicals. Now let us see what are these carbon free radicals about. Okay, they can also be once defined that carbon free radical. I'm talking in later stages. If I use the word free radical, please refer it to only carbon free radicals. Now, in case of carbon free radicals, I can say that the carbon is surrounded by 7 electrons, out of which 6 are bonded electrons and 1 is unpaired electron. Okay, so general representation is like this. Correct? So 6 will be the bonded electrons and 1 will be the non-bonded unpaired electron on it. Now, it is formed by homolytic bond fissions. It is formed by homolytic bond fissions. We have seen it beforehand only that when there is a less energy gap or conditions are gaseous, then we'll have homolytic bond fissions like this. This homolytic bond fissions can be achieved either by the help of photons or by the heat or by some redox. So it is a possible phenomena. It is achieved by these. A very important point is again hybridization. Hybridization of free radicals. You might expect that their hybridization should be sp2, but there is no such fixed behavior related to hybridization of free radicals. Okay, hybridization of free radicals could be sp2, could be sp3. Sp is rare. I would put this as a rare, but this is very common. It could be sp2, it could be sp3. For example, when I talk about, say, this, okay, if the unpaired electron present, if the unpaired electron present in this particular carbon is in a hybrid orbital, it will become sp3. If it is present in an unhybridized orbital, empty p orbital, MTK, available p orbital, then it will become sp2. So what is the factor that is used to confirm that what type of shape it, what type of hybridization it will be in? Is it going to be sp2 or is it going to be sp3? Okay, which uh, type of hybridization should be assigned to it? So what happens is we have studied through our several methods that shape of the different free radicals. If this is sp2, then its shape and arrangement should be found planar. Okay, and if it is going to be sp3, then its shape is to be found like this, pyramidal. And shape can be confirmed through spectroscopy, bond angles can be confirmed. Okay, so using those bond angles and shapes, it is found that, okay, please mark this as important, it is found that CH3 dot to CH2F dot to CHF2 dot and then to CF3 dot with increase in number of fluorines. Okay, with increase in number of fluorines, it is found that the hybridization shifts from sp2 to sp3. From here to here, percentage S in hybrid orbital decreases. When we move from SCH3 dot to CF3 dot, the percentage in hybrid orbitals decreases. Okay, so this is sp2, this is sp3, and these are intermediate between sp2 and sp3. So here you can say bond angle is 120 degree. Here you have to say it is somewhere 109 degree 28 minutes, or rather less slightly due to bent pyramidal structures. And to remember, please remember that as and as the subsequent electronegativity increases, the bond angle is being decreased and the percentage S is also being decreased. Okay, is that clear? Now, if I go to generalization, general, if carbon is attached to carbons, is attached to hydrogens, then generally hybridizations are sp2. Okay, if it is attached to carbons and hydrogens, then it is sp2. But if we are having a radical at bridgehead, then this is also sp3, because otherwise it can't be formed. If I having a bridgehead or I having a condition like this, no possibility that it can be planar. So it has a possibility of both. You cannot fix that this is the only and this is the fixed hybridization for a radical. But if carbon is attached to an atom A, where A is second period electronegative atom like F, okay, O or N, then take sp3. I hope I have made my point very clear. When do you have to take it as sp2 and when to take it sp3? There is no fixed hybridization in case of free radicals. Okay, and also remember this point, like carbocations, pH3C dot here is also propeller shaped. Here also that particular type of radical is propeller shaped, and because of the steric and similar behaviors, it is propeller shaped. Broadly, I can say the factors affecting the stability of free radicals are same as carbocation, but that certainly is not always true. Okay, that certainly is not always true. I would like you to remember it as an exception that a radical, please remember this is an exception compulsorily, a radical alpha to carbonyl or to NO or to ester linkage, okay, or to cyno are exceptionally stable, are exceptionally stable. Similarly, radicals which are formed adjacent to atom with lone pair are also very stable. These 2 points clearly indicate that you cannot go by the direct and generalized rule that radicals can behave always like carbocation. They are close, that is okay. Okay, as far as inductive and other factors are there, it is okay. But these two are entire different observations. Please mark them in your notebooks and keep it in your brain that dot, that is free radical, adjacent to these strong minus R groups, NO, NO2, CO, ester, CN, etc. I should put the word etc. are exceptionally stable. And the dot adjacent to some second period element with lone pair are also very, very stable. Okay, is that okay? Now let's move to carbines. Carbines are represented as either this or this. Okay, carbines are reaction intermediate in which carbon is surrounded by 7 electrons. Oh, sorry, 6 electrons. Surrounded by 6 electrons. Out of these, 4 are bonded electrons, 2 are non bonded. Now, these 2 non bonded electrons either exist in the form of pair of electron or 2 unpaired electrons. When they are in the form of pair of electrons, then it is called singlet carbene. When they exist as unpaired electron, then they are called triplet carbene. Okay, so based on the arrangement, they are like this. In case of triplet carbene, this bond angle is towards 136. In singlet, it is like 103. Okay. Now, what is the difference? How they are formed? Basically, carbines are formed by 1, 1 eliminations. Okay, let me tell you some formations. If I have CH2 double bond N, what is this? This is diazomethane. This is diazomethane. If I heat it or I put a photon, I incident a photon on this, then it breaks into carbene. Nitrogen is released. Example number 2, if I had ketene by similar method, I can have carbene. We can have carbene from chloroform type things by the use of strong base. First, there will be formation of anion, and then this anion breaks further and a carbene is formed. So there are several different sources of carbines. Okay, besides this also there are several methods. It is not that just these are the methods, but I just exemplified few where carbene is formed during the reactions. Okay, one particular very different method for carbene formation, I would like to show you one more. See here. If I have this type of structure and I irradiate it with H nu. Okay, you can see here aromaticity can come. So these bonds will break and a pi bond coming here will make this ring aromatic. And this part will form the carbene. Okay, you can have a carbene if you heat strongly an ion of trichloroacetic acid. Okay, if I heat it very strongly, I will first get CCl3 minus and CO2, and then this will go to carbene, releasing Cl minus. Okay, so there are so many other methods. And then carbene can have both electrophilic, nucleophilic, as well as the radical reactions. After carbene, we move to nitrene. Nitrene is similar to carbene, formed in a similar way, and it also has singlet triplet nomenclature. This nomenclature is basically derived from spectroscopy. This is singlet nitrene, this is triplet nitrene. Okay, here also the um, definition of the intermediate is also similar. Here, nitrogen is surrounded by 6 electrons, 2 bonded electrons and 4 non-bonded electrons. Okay, those 4 non-bonded electrons can be as 2 pairs of electrons, then it is singlet, or it could be 1 pair and 2 unpaired electrons, then it is called triplet. Nitrene reactions, we do not form direct nitrene in most of the reaction, but they are involved in certain reactions like Huffman bromide rearrangement, Schmidt rearrangement, Curtius degradation, etc. Okay, and then we move to the last set, that is benzene. Benzene as such is not in JEE syllabus, but just have a general idea. These type of arrangements are called benzene. Okay, it exists either as a biradical or it can exist as a Zwitter ion, plus and minus heterolytic fission of that pi bond. Okay, it is formed, say for example, if I have N2 plus, if I had CO structures like this, when I heat it, benzenes are formed. This is just one example of its formation. Huh? We can have so many. If I had bromine and bromine, magnesium, diether, benzene can be formed, etc. The important point that you need to remember about benzene is all carbons in benzene are sp2 hybridized. Okay, none is sp hybridized. All are sp2 hybridized, and benzene is also aromatic, though unstable, but is still aromatic. This part is not of the resonance cloud, but this creates an aromatic cloud. So it is very much aromatic. Okay, so we end our discussion of uh, reaction intermediates here. You please go through the lecture, read reaction intermediates. The carbocation rearrangement is something which is very important and we'll certainly cover when we'll proceed into coming reaction mechanism chapters. Okay, this was a general introduction to reaction intermediates and their stability. So, okay, keep learning.